in some sense, informally, we've already been kind of talking about sets. You know, when we were talking about open statements, we were talking about the universe and things like that. Really, like the universe of a open statement or something, really that was always a set, right? But formally, we're going to now talk about what a set is and things like that. Well, not that formally, but I'll get to that in a second. So somewhat, yeah, maybe I'll say somewhat informally, a set is a collection of objects. Okay, these objects could be, I mean, often it's, numbers or, it could be really any sort of mathematical object. So it could even be sets of sets, or it could be anything really, letters, etc. So it's a collection of objects, and those objects are called the elements of the set. So a set is just a collection of elements. Okay. We usually, so the notation for sets, so we denote sets using these kind of curly brackets, like, these things, right? So, for example, if I take 1, 2, 7, 8, so that's a set with 4 elements, right? The elements, the elements are the number 1, the number 2, the number 7, and the number 8. Okay, but the elements of a set don't have to be numbers, so I could write A, B, 8, @ symbol, smiley face, right? And this is a set with 5 elements. Okay, so is the basic definition clear here? Okay. Okay, so on an kind of an intuitive level, like this definition, so this definition is, for the purposes of this course, this definition is correct, and this is what you should always kind of think of as a set. And actually, as a mathematician, like in my day-to-day, when I'm doing mathematics, 99% of the time, I think of a set as something like this, right? I think most mathematicians would agree. But I should mention that technically this definition is garbage in some sense. Because, and we might see it, if we have time next week, I'll show you some paradoxes, or one paradox in particular, which actually shows that if you think about sets in terms of this definition, then formally it leads to a contradiction, which is bad news, right? If you think of sets this way and it leads to a contradiction, then this must be a really bad definition. Okay. But like I said, for all intents and purposes, like we don't need to know the formal definition of sets, but we will see how this does have problems. Yeah, hopefully next week I'll show you that. But like I say, for the purposes of this course, this definition is totally fine. Okay, so hopefully that doesn't confuse you. But okay, any questions about sets? We're still okay with sets? Okay, so what I wanted to say, okay, I have a bunch of things to say. So one thing is that the order of the elements in a set doesn't matter. So the order that you list the elements doesn't matter. And also, repeated elements don't matter. That is when we're talking about sets. The order doesn't matter, repetitions don't matter. So if I take, for example, 1, 3, 5, 7, it's the same, it's regarded as the same set as 7, 1, 5, 3. Right? So if I write the elements in a different order, it doesn't matter. And the same as 1, 1, 3, 3, 7, 7, 7, 5. Yeah. Exactly, yeah. So I would say that this set has 4 elements. Even though it looks like it has 1, 2, 3, 4, 5, 6, 7, 8, it has 4 elements because it's got a whole bunch of repeats. And so in particular, it should have the same number of elements as 1, 3, 5, 7. The only way for that to make sense is if we say it has 4 elements, right? If I'm saying that this set is the same as this set, and this one has 4 elements, then that one better also have 4 elements in some sense. So yeah, that's a great question, actually. Any other questions? I could even write infinitely many repeated ones, right? And it would be the same set. You know, it doesn't even matter that it's finite. Okay. So one thing, so yeah, I mean, a lot of the time we end up dealing with sets whose elements are numbers. They don't have to be numbers, like I said. You know, here we've got the @ sign and smiley face A, B. But you can even have sets of sets. So, and we'll talk about this sets of sets actually next week in more depth. But so you can even have sets of sets. So for example, I could take the set containing the set 1, 2, and the set 3, 4, and the set 5, and the set 1, 2, 3. Okay. How many elements does this set have? 4. Yeah, exactly. So in particular, the number is 4. It's not 1, 2, 3, 4, 5, 6, 7, 8, right? So this has 4 elements. Because if I count the elements of this set, you know, this set contains 4 sets. And I don't care how many elements those sets have. I just care that, yeah, the whole thing, you know, the big set has 4 elements. So in particular, you know, this set, so in particular 5 is not an element of this set, but the set containing 5 is. These are things that confuse a lot of people, so I mean, even if to some of you this seems clear, I guarantee that, yeah, there are people who will get confused on this on tests. But is it clear what I mean by this? Like, this set contains the set containing 5, but this big set doesn't contain the number 5 by itself. Okay. This is a bit weird, but yeah. Yeah. Oh, that's a good question. So the elements of a set, they don't have to be all the same type of thing. So I could also take the set containing like, so if, if my set contains some sets, that doesn't mean it can't also contain numbers. So it can be this, the set containing 1, 2. I can also take the set containing 1, 2. I can take, Z, right? So you can have a mixture of all kinds of things in a set. Yeah, that's a good question.
And that's 4 elements, right?
Exactly. Yeah. Now, of course, if I threw in like this set 2, 1, still 4 elements, because even though these look different, these are the same, right? Because we say order doesn't matter in sets. So these are the same. And when you have you have repeated elements, it doesn't count, right, as extra. Okay. So a lot of this is just really convention, right? We're just kind of learning what are the rules of sets in some sense. Okay. One thing is like all the sets we've drawn so far are just finite. And not only are they finite, but they're pretty small. What if you wanted to write the elements of a really big set or even an infinite set? So there's several ways of doing that. One way, which is kind of informal in a certain sense, is to just use like ... So if I write, the set of positive integers, so I could write just 1, 2, 3, 4, ... And then hopefully it's clear, like, I mean, this goes on forever. Now, like, you have to be careful with doing these ... things because, I mean, sometimes it might not be clear. Like if I just wrote 1 ... what set is that? I have no idea. I mean, this could be the set of all odd numbers. It could be the set of all positive integers. It could be, it could be the set 1, 5, 25, powers of 5. I mean, this is no good, right? Don't write this because nobody knows what you're talking about. This technically, maybe somebody could argue, I don't know what you're talking about, but it's kind of clear, right? We're hitting every number. If I wrote something like 2, 4, I feel like this is not quite clear enough because it could be the even numbers, or I don't know, maybe it could be powers of 2. Which of these is it? I don't have like a hard and fast rule for like how many elements you need to write, but yeah. The point is to try to communicate clearly, okay? So if it helps to write one more element of your set before doing the ... then then write it. By the way, this also works for finite sets, right? If I write the set of 1, 2, 3 up to 120, right? This is all numbers, integers from 1 to 120. Right, so you don't have to write 120 numbers to write that set. I can also do things like 0, 1, 2, 3, ... and then -1, -2, -3, ... in that direction. And this is the set of all integers, right? Any questions about this? Okay. So yeah, like I say, so this, what is the word that's used for this? Like, they call this like an implicit listing in the notes. when you write it with these kind of dot, dot, dot things. Okay. A more formal way of writing, big sets or even small sets is something called set builder notation. So the kind of way that this works is, well, maybe I'll give you an example and then I'll explain more generally what it means. But for example, I could write the set of all x such that x squared minus 7x plus 12 is 0. So the colon here, you should read as such that. Okay. And some people use, so you may see this, you may come across this in the future. So instead of the colon, some people just use a straight line, but I think we'll always use the colon. So, the way you should interpret this is, I'm saying that the set of all x such that this condition holds, right? So I'm saying all x such that it's the open statement x squared minus 7x plus 12 equals 0 evaluates to true. Okay. So typically, when you kind of use this notation, there's a sort of, so typically there's a sort of universe. So here I'm perhaps, I should say probably that the universe is the real numbers or something like that. Or, so there's a universe. Maybe it's not always specified, but maybe it's clear from context. So either clear from context or specified. And the way you write this set, and px is an open statement. For example, the open statement x squared minus 7x plus 12 is 0. And you write the set as x such that px. Which, you should take this to mean the set of all x in the universe such that px is true. By the way, what would this set be? A kind of easier way of writing the same set. Exactly. So this is a slightly complicated way of writing the numbers 3 and 4, right? Is it clear that this is the same thing, right? Because the solutions to this equation are 3 and 4. So the set of all x such that x squared minus 7x plus 12 is 0 is the set 3, 4. Is this weird? Are there any questions about this? So there's something kind of nice about this set builder notation, which is that, you don't really need to know explicitly, you can write it down without knowing what the set is in some sense, right? Because, okay, we were able to factor this quadratic, but suppose we didn't know how, we could still write this set and this still makes sense, right? For example, I can write the set, the set of all n such that n is prime and n plus 2 is prime. Okay. Now this is a set of numbers, but I have no idea what this set is. In fact, I don't even know if this set is finite or infinite, and nobody does. So, it's a major open problem. To just ask, is this set finite or infinite? Right? But even without knowing the answer to this, I can still write the set, right? I just don't know how big it is. So I can say that, for example, 3 is an element. So if I call this set S, I can say 3 is an element of S. That's true because 3 is prime and 5 is prime. So any questions about anything so far? It's maybe a problem with 8:30 classes. I think everyone's very tired. I know I am, but yeah. Okay, so basically, what you really need to know here is, like, if you see sets written in this way, you need to be able to interpret what that means. You know, this fact that it's all n, the colon means such that, and this statement is true, right? That's the kind of key thing here. And if you're asked to write a set in this set builder notation, you need to know how to write it. So that's kind of the key thing. So now let me tell you a few things you probably already know, although you might not know the notation. Well, actually, we mentioned this before slightly or briefly, but so let's talk about some special sets. So this n with the kind of extra line is the set. Well, maybe I'll just write it with some of this notation we've developed. It's just 1, 2, 3, 4, ... Or in other words, the set of all positive integers. Okay. Z with an extra line. If you look in the textbook or in the notes, you'll see these are typeset in some special kind of font, right? Which kind of looks like this. So this is the set of all integers, positive or negative. Q is the set of all rational numbers. So this is going to be does anyone have we've talked about rational numbers, right? When we were proving root 2 is irrational. What's a good way to write Q? Any thoughts? I'm going to write it with the set builder notation. This, with the colon, right? Any thoughts? Yeah. Something like that, yeah. So I'll maybe do it in a slightly different way. For some reason, I guess I'm brought up in, mathematically to think n is always an integer, but that's kind of arbitrary. So in some sense, you're right. It's all the things which are a over b, but such that a and b are integers. That's one key thing to add. I'll actually just write this like this. It's all a over b such that a and b are in z and b is not 0. That's another technicality, right? We need to avoid dividing by 0, but yeah. Oh, I didn't introduce this notation, sorry. So let me just say a, I'll introduce that notation in a minute, but a and b are elements of z, and b is non-zero. Sorry about that. And R, well, it's a set of all real numbers. I don't really have a better way to say that using what we've developed so far. So I'll just say that this is the set of real numbers. And we'll sort of assume we understand what that means, even though it's not really that clear what is a real number. But, well, that's in some sense, that's a way to define it. But then you have to first define complex number, which makes your life, hard as well. Well, and since we're talking about complex numbers, let me define them as well. So C is the set of all A plus BI such that A and B are real, meaning they're real numbers, where I is square root of -1. So this is complex numbers. Okay. Any questions about any of these? Okay. Basically, you need to recognize these symbols and know what they mean. So let me now introduce some notation that I accidentally used when I was defining the rationals. So we're going to introduce this notation. It's like a weird kind of E thing, and it means is an element of. So if S is a set, if I write X is in S, that means X is an element of S. So when I was defining Q, or the rationals, what I wrote was, because I use this notation every day, so it's just instinctively what I do, right? So I write A over B such that A and B are elements of Z, and B is not 0. Right, so it's a bit of a more compact way of writing the same thing. Can anyone give me a good way of writing the complex numbers using this like element notation? Exactly, yeah. That's exactly what I was looking for. So A plus BI such that, remember, colon means such that A, B are in the reals. So yeah, it's just kind of a nice way of writing things, I mean, it's a lot faster than keep having to repeatedly write is an element of, right? You can just write this. Yep. That's a good question. Yeah. So here I didn't say anything about I. In some sense, it's really gotta, it depends what context you're in. So if you are writing this in the context where everybody who's going to read it knows what you mean, then it's probably okay to just write I. But yeah, for the purposes of this, I probably should say where I is the square root of -1, and kind of write that outside of the set to just clarify that that's what I mean by I. But yeah, that's a very good point. All of these things are just methods of communication, right? So it very much does depend on the context. Any other questions? Okay. Okay, let's play around with some of these definitions. So let's do a bit of kind of practice, see if we understand what's going on. So let's say I write, I let S be the set 1, 2, 1, 2, 3, 4, 5, alpha, infinity. So a bunch of kind of true or false questions. So true or false. So is 1 in S, is 3 in S, is 1, 2 in S. Do I have any more interesting questions? Maybe not. Okay. What's the answer to the first one? Right. 1 is in S because you can just see it. Oh, maybe I'll ask another one. I've got another good one. So okay. So this one's true because 1 is right there. Second one, how come? Yeah. This is really just showing, kind of illustrating the distinction between, the number 3 is not in this set, even though the number 3 is inside of a set that is inside that set. Those are very different things. So indeed, this is false. 1, 2, true, right? Because 1, 2 is an element of the set. It's right there. 3, 4, no, right? How come? I guess there's not really a good reason. This is not in S because it's not in S, right? It's none of these elements, that is not 3, 4, that's not 3, 4, that's not 3, 4, that's still not 3, 4, neither is that or that. So that's false. What about the last one? Yeah. How come? Exactly, yeah. So this one's true because even if it looks different, this is the same as that set. 3, 4, 5 is the same as 3, 5, 4, 4 because order doesn't matter and repetition doesn't matter. So therefore, this is the same as that. Therefore, since this one is an element of S, this set is an element of S because they're the same set. Okay. So maybe this is the only weird one, but we got it. Okay. Here's a question. What does it mean for two sets to be the same, or for two sets to be equal? So I guess like we've thought about that informally, right? That they have the same. I mean, we know that if two sets have the elements in different order, they're the same. And if they have repeated elements, the repeats don't count. But that doesn't quite tell us what does it mean in general for two sets to be the same set. So what does it mean for sets to be equal? So let A and B be sets. And, well, we say that A is equal to B if, and then I want to finish the sentence. I don't know. I mean, does anyone want to guess what it means? Like, how would you say? And remember, these could be finite. If these are finite sets, then I think it's pretty easy to say if they're the same. But these could be infinite sets. These could be anything, right? But yeah. So, any thoughts? Well, the short answer is that two sets are the same if they've got all the same elements. Well, so informally, if they have the same elements. But what does that really mean? So what it means is that if I write x in A, that this is logically equivalent to the statement x in B. So in other words, to show that A is equal to B, what you want to do is show that, what you need to show is that to show is that if X is in A, then X is also in B. So there's kind of two directions, right? And if X is in B, then X is in A. Yeah. Yeah. Sorry, what was the actual question? Yeah. For example, okay, let's say A is equal to the set containing the set 1, and let's say B is equal to the set 1. Is this the kind of example you're thinking of, or? Because this would kind of be like the set B is inside of A, but these would not be the same because they don't have the same elements. So it's always about, yeah, so that's something to keep clear, is that we're comparing the elements of the sets, not necessarily the elements of the sets inside of the sets and things like that. So here A is not equal to B. And I think, yeah, there's going to be no way to, well, if I tried to change this to make them equal, we're going to run into things which are going to actually show us these paradoxes. I don't want to get there yet. Yeah. That is very much getting, if I write A to be the set containing A, this could get problematic. Let's not think of this right now. So let's not consider this sort of thing. But this concept of, in some sense, this is coming to like this issue of self-reference. Can a set, in its definition, reference itself? Which is very problematic, and it gets into paradoxes, which we don't want to do. But yeah, these are very good questions. I mean, these paradoxes and things like that get into things that were like really troubling people for decades at the beginning of the 20th century, because they, basically it was our whole concept of what a set is totally wrong because it leads to contradictions, and people were very troubled by that, obviously, because maybe all of mathematics is wrong if our definition of set is wrong. But eventually they figured it out. So yeah, let's not talk too much about that. But yeah, let's I guess get back to what does it mean for A to equal B. But these are awesome questions. But yeah, right. So in practice, what you have to do, so if somebody says prove A is equal to B, what you have to do, you have to take an arbitrary element of A, so any element of A, and show it is also in B. And then if you can show that any element of B, any element of B is also in A, then you can say, therefore, I mean, you wouldn't necessarily have to say this, but therefore A and B have the same elements, and so they are equal. And that actually kind of makes sense with this whole repetition, reordering stuff we talked about before. Because if I take the set 1, 2, 3, and I take the set 1, 1, 2, 2, 3, 3, 3, if you take any element of this set, like 1, you can clearly see that it's also contained in this set. And any element of this set is also contained in this set. So therefore, by this definition of equals, these are equal, because every element here is also here, and every element here is also here. Yep. Oh, total. Yeah, no, it makes no difference. So this would also be the same as 1, 2, 1, 3, 1, 1, 3, 3, for example. Yeah. So equality for sets is this is the kind of only thing you have to care about, that anything here is also here, and anything here is also here. Doesn't matter how many times it appears or anything, or what order. Just everything here is here, everything here is here. Okay. Any questions about that? Okay, let me just, I'll say a few more basic things. I mean, we're just building up definitions. We'll get more and more practice with these definitions as we go, but I kind of realized that this is kind of a lot of information, but hopefully it's not too bad. So the cardinality or, you know, size of a set, well, let me just say, let's stick to finite sets for now. So a finite set is the number of distinct elements that it contains. So when I say distinct, I mean, again, that repeats don't count. And the notation for cardinality is kind of like absolute value. So let's say I'm talking about a finite set S, right? Then the notation is like, you know, vertical lines around S. So for example, the cardinality or the size of ABC is 3. But also if I do something like A, B, B, A, C, A, B, well, what's the cardinality of that? Right, 3. It's 3 because we don't count repetition. Now, as you can imagine, like, okay, like the cardinality of a finite set is not that complicated, right? I mean, just look at how many things it has, count them up, and that's the cardinality. Obviously, when you're dealing with infinite sets, okay, well, actually, maybe it's not obvious, but we're going to see later in the course, probably pretty close to the end, some things about cardinalities of infinite sets, right? So one question is, suppose I take 2 infinite sets, do they have the same size? Or could they have different sizes in some sense? Like, for example, the integers is infinite. The real numbers are infinite. But are they the same size? One seems bigger than the other, right? Anyway, that's for later, much later in the course. For now, all we need to know is what's the size of a finite set, which, yeah, this is the notation. Any questions about this? Also, so maybe just to mix this with our other notation a little bit, right? So what if I write the cardinality of the set X? And let's say I'm kind of dealing with the universe being the reals, such that x squared minus, well, let's say x squared minus 4 is 0. How big is this set? Oh, 2. How come? What are the elements? Right. Is that clear why this is 2? Right? Because this is just the same as the cardinality of negative 2, 2, which is 2. What if I write this? The cardinality of the real numbers such that x squared plus 1 is 0. 0. Indeed, because there are no such things. This kind of brings up something we haven't talked about, which is that a set can have 0 elements. So a set can be empty. So the empty set is denoted with a 0, kind of a 0 with a slash kind of thing. right? And it's the set that just doesn't have any elements. Okay, so this is the empty set. Yeah. I mean, this is a weird way of writing the empty set, but it's the empty set, right? Because there are no x in the reals such that x squared plus 1 is 0. Okay, we'll keep playing with these definitions more next time. But yeah, see you guys on Thursday. Okay, so okay, so remember we're talking about sets, right? So just to remember, it's been a long time since because we had the holiday on Thursday. So I wanted to remind you a set, right? A set is just a collection of things, and the things in the set are called the elements of the set. So, and usually we write sets with these curly brackets, right? So if S is 1, 3, 7, then that's a set, and the elements are 1, 3, and 7. For example, I could write also something like 1, 3, 5, 7, ... Which maybe actually no, it is kind of it's fairly clear, right? So this would be the set of positive odd integers, right? So we kind of introduced various different notations for sets, right? You can just list the elements. You can put a ... thing. And then we had set builder notation. So if I say the set of all x such that x squared, well, let's say I say, to make it clearer, say the set of all x in the reals such that x squared is 4. Well, that's negative 2, 2, right? So remember, this is just all this notation stuff. Another kind of reminder, so let A and B be sets. Does anyone remember technically what it means for A to equal B? Yep, totally, yeah. So kind of, yeah, maybe in somewhat informal terms, it's exactly that, right? It means that A and B have the same elements. If I want to write that really kind of with this kind of logical notation and whatnot, I can write that it means that if, that the statement that x is in A is logically equivalent to x being in B. But that totally just means, in other words, like A and B have the same elements. Okay, or you could think of that in some sort of two statements, like every element of A is also an element of B. That's this kind of implication, right? And this implication is like every element of B is an element of A. And so together, that means that they have the same elements. Okay. Any questions about this? Okay. Well, now, okay, so this is like a logical equivalence, right? I mean, what would it mean if this logical, instead of a logical equivalence, we have a logical implication going in one direction? So that's the concept we're going to define next. So definition. So as usual, A and B are going to be sets. So we say that A is a subset of B if whenever x is in A, then x is in B. Or in other words, like formally what I'm saying is, yeah, the condition, x being in A logically implies x is in B. So it kind of, informally, just using, in English, really what this means is that every element of A is an element of B, but the elements of B might not be elements of A, right? But not vice versa. Vice versa means, right, if I switch A and B, that's not necessarily true. And the notation for this is, so it's this kind of elongated C looking thing with a line underneath. Okay. So the way you should read this is like, this means, well, when you kind of see this symbol, you read it as is a subset of. So this is like A is a subset of B. Okay. So the picture for this is like, you should imagine B is some set. If A is a subset of B, what it means is that A is kind of inside of B. So every element of A is an element of B. But there could be some elements of B which are not in A. So this is the kind of general picture. Although we're not saying necessarily that there has to be elements of B that are not in A. So note that, like, if the sets are the same, like A is a subset of itself, right? Because if you check the condition here, it is true that if X is in A, then X is in A. So for every set A is a subset of itself. So but yeah. Okay. Any questions about that definition? So it's just a concept of one set being inside of another set. Okay, well, let's see how well we really understand this. We've given a lot of notation last time and this time. So let's test it a little bit. So this is going to be mostly true-false questions. Okay, so first of all, I'm going to let S be the set containing A, B, the set containing 1. Remember this weird thing that sets can contain sets. 7, 8. 8, 9, 7. I'll throw in that. And also this. Okay. So, okay, true or false? Okay, I'll just write them and then we can think about them. So I'm really kind of trying to explain here the difference between element of and subset of, remember? So, and okay, this one's not a true or false one, but also I want to know what's the size of S. So remember, in case you've forgotten this notation, right? If I write X is in S means, X is an element of S. So, so true or false? The first one, true. Let's have a show of hands. Who thinks it's true? Who thinks it's false? And then anyone else doesn't care, or hasn't formed an opinion yet. That's fine. So okay, yeah. So I think the majority wins here. Yeah. So this is true. So this is asking, is A an element of S? And you can just look and see, oh, it's right there. So yeah, it's definite. A is definitely an element of S. That's a good one. What about this one? Yeah. How come? Exactly, yeah. I mean, this one's kind of false because it doesn't even make much sense. Like, to say that something's a subset, like this should be a set, but this is just an element. Like, this, this doesn't really make any sense in some sense. But that's exactly what I was looking for. Okay, how about this one? Is the set containing 1 a subset of S? How come? So, so that part of it is okay. This statement makes sense because this is a set. That's true. But is it really a subset? So remember, we have to go back to our definition of subset, right? So it's a subset if every element of that set is also an element of the other set. Yeah, and so this is one that people get caught on all the time, right? It looks like the answer should be yes because you can kind of see it there. First of all, this is a set, so this makes sense, this statement, and you can see it there. But it's not a subset because it's not, if I look at the element of that set, 1, that element does not appear in S. So the set containing the number 1 is different than the number 1. So this one's actually false. Yep.
So does that mean 1 has, like, if it were to be true, then 1 would be outside of the curly bracket?
Exactly.
Okay.
Yeah. Yeah. So when you're doing subsets, you're really comparing the elements of the set on the left to the elements of S. And yeah, this thing with curly brackets is not an element of this set. It is the set. It's like, yeah. You think of the set as being like a sort of bucket containing elements, right? S contains a bucket that contains 1, but S doesn't contain the number 1. And those are different things. How about this one? I've got everybody scared because yeah. How come? Yeah, there's not really more of a reason that you can give than that. It's just right here, so it definitely is true. So this is an element of S. It's not a subset, but it is an element. How about this one? I've got heads shaking. So this is indeed false for those of you shaking your heads, but does anyone have a reason why it's false? Yeah, exactly. So the elements A and B are here, but this question is asking, is it true that the set AB is an element of S? For that to be true, you'd have to see, like, in this list, you'd have to see the set AB. So this is asking, is that in the list? And even though A and B are in the set AB, by as its own thing, is not there. So this one's false. This one, right? This one's true because A and B are, each element of this set is in this set, so that's true. How about this one? How come? So let's do a kind of vote. So on the count of 3, everyone, if you want to, answer true or false for this one. So 1, 2, 3. Okay, so it wasn't unanimous, but I think more people said true. It is true because, well, the question here is asking, is it true that every element of this set is an element of S? So if I look at there's only one element, right? The element is the set 987. I need to check, is this an element of S? Okay, so it's not that one, it's not that one, it's not that one, it's not that one. It could be that one, right? Now, you can see that the numbers are sort of scrambled here. But that doesn't matter, right? Because we said in sets, the order of the elements doesn't matter. So 987, the set 987, is the same as 897, right? Because the order of the elements doesn't matter. So it is true that this set, or this element, is an element of S because it's the same as this. So these sets are the same, therefore, this is true. Okay. And now the question, how big is S? Like remember these bars mean cardinality, so it means the number of elements of S. Okay. 5, yeah, that could be the answer. Any other thoughts? Okay. Yeah, so where do you get 5 from?
Because 5 is number of
I think you're probably right. So if I count them, A, okay, that's something I haven't seen before. 1, 2, 3, 4. Okay, these are all, the first 5 things are all different. Then I look at A, I've seen it before, so that doesn't count. Repeats don't count. And then I guess the trickier one is 8, 7, right? And technically I've seen that before because I saw 7, 8, and those are the same set. So I agree that the answer here is 5. Okay, but yeah, I think people could have been tricked into thinking it's 7 or 6, right? Especially not noticing this is easy, but or like it's easy to miss that. But indeed, yeah, the answer is 5. So you're always counting distinct elements when you compute the cardinality. Okay. Any questions about any of this?
So why?
I am counting the one with the 9 in it. So I'm counting this one, 1, 2, 3, 4, 5. But this one is the same as this, and this is the same as this. So these don't count extra. So those are my 5 things. Yeah. Any other questions? This is probably the thing that people get confused and mixed up on more than anything, is this like sets containing sets and what that means. So if you keep it straight that like what the difference between an element and a subset, that's going to help you a lot. That's a good question. Yep. And in this case, it is the case. Yeah. So if I write brackets 1, that's true. It's true because essentially because this is true. So and this is the only element of that set. But that's a very good question. Yeah.